Okay, now let's get started. Today we're going to talk a little bit about lecture 10, right? So heading into chapter 6, right? As you can see that this course is structured very closely, as we said in the beginning, right? Follow very closely for the open book, right? In fact, the book was written precisely for a course like this, right? Very much, we have 2 weeks per chapter. Very much we're going that way, right? Roughly, each chapter takes about 2 weeks lecture, right? 2 lectures, and I mean mega lecture. By one lecture, I mean lecture for entire week, right? So we kind of follow this kind of the pace. Again, it's a very technically, as I said in the previous lecture, right? The course meant to be technically, information-wise, extremely dense. Okay, strat across many different fields, and pretty large historical span of development of the ideas across several main fields, right? Information theory, optimization, signal processing, and control, and machine learning, and so on, and deep learning, and so on, right? And also that across a very large historical span, right? As you can see, many of those ideas were developed through at least, if not decades at least, sometimes, hundreds of years or decades at least. The ideas evolved from traditional fields. So mastering all of that requires diligence and a lot of dedication and focus. However, nevertheless, as I said, right, although technically dense, but I want to make sure it's conceptually simple, unifying, okay? And by the end of this day, by the end of this course, I want you to understand all the different threads, a lot of pieces, technical pieces were developed in the history in different isolated fields, right? Separate or some rediscovered, reinvented multiple times in different fields, right? They probably serve a common purpose, right? They're just a slightly different versions of the same thing, right? Even the classical analytic approach, right, to model data, to model the low-dimensional structure in the data that you're familiar with in signal processing, in control, right? In information theory, Gaussians, subspaces, linear models, linear dynamical systems, mixture of linear models, and so on, right? And denoising, filtering, prediction, right? All the classical methods, even physics, physical equations, right? All capture the same thing, analytical equations, describing laws, physical laws, and in, analytic forms. And also the modern practice, data-driven, empirical approach, right? They're pursuing the same thing, right? And the computational approach to things, right? So you want to reach that conceptual simplicity, understanding, right? Understand there are just different variants, right? Or special cases of the same thing, right? So this is exactly the purpose of the course, right? Hence, clarify all the mysteries. If you don't clarify, right? And all those different threads, different things will confuse you. You think they're different. They're working on different things, right? So this is actually the thing. Before we begin, right, this is where towards the end of the course, last few lectures, and we'll have our final homework that this Wednesday will be released by TA, and probably primarily will be some kind of programming based. As I said, towards the end, we are trying to bridge the concept and theory to practice. So the more, and the last homework and also the final project is really for you to apply, right? To use what you have learned in class. Not only the knowledge, but also the methodology, right? As I said, knowledge these days is cheap. Methodology is expensive, okay? It's powerful. Right? Try to exercise that. Final project will be due on early December, presentation and the final project. So you have probably exactly 1 month, okay? All right, try to make use of it. Right? So one thing, guys, what is the most common problem with graduate students? They procrastinate, okay? Yeah. 拖延症, right? And I still have, and then just like that's why there's a joke, right? We said deadline is 生产力, right? Whenever there's a deadline, right? Conference deadline is many of the students don't even work until the 1 week before the deadline, right? So don't do that, right? If you want to be better than most people, if you really try to plan things, do things quickly, do things in advance, right? So don't be as many others, okay? This is not time good for that. And you have 1 month. Again, working with a team member, be critical, right? Try to learn something. Okay, the purpose is not that you try to, honestly, I do not expect any of you to produce anything new, okay? Trust me, I don't, right? That's maybe a very high hope, right? I want you to learn something. Learn something about the field, learn something about the method. Learn something new that you previously were not aware, right? So then the process will be worthwhile, okay? That's the purpose, right? And even in your final report what mistake you made. And you discover something you didn't know, okay? Try something, right? It's your own idea, right? Try to be critical about things, right? So that's actually the idea. Now, let's do a summary, right? As we towards the end of the course, we'll probably do a few summary. What this course we have done so far, right? So first chapter, we talk about the history of the study of intelligence, understanding the history of intelligence, right? Since the beginning of life, right? And also, the different phases of intelligences, right? From very early primitive life, DNA, to memory, brain, to social intelligence, human societies and civilizations, and also to science, right? So this is a different way. And also till about 80 years ago, 1940s, people started to try to uncover the computational mechanism of intelligence and try to use machine to mimic. The imitation games has started, right? Try to imitate intelligence. So that's sort of what we did first. And also through that study, through that understanding the history, evolution of intelligence, we kind of understand what the intelligence is trying to do, what's in common. Although there's differences in the different stages of intelligence, but there's something rather in common. They all try to learn what's useful in the form of knowledge or memory. Help the life to predict the world, outside the world, to build a model for the external world, right? So they can predict what's going to happen, hence plan their actions around it, right? Make better decisions. And then we talk about then what is predictable information? What is useful information? What is knowledge? We attempt to try to define that mathematically, right? Hence, one of the forms is that all the predictable knowledge or phenomena or data that carry useful information allows you to do better prediction are always in the form of the structure, has low-dimensional structures in data, right? They're not random. They don't fill the entire space of the vision space. They have very, very good follow physical laws, are described by equations, right? Even they cannot describe by equations, then we can build a memory around it. And our memory precisely captures those low-dimensional structures, right? Through compression, through denoising. Get rid of noise so that I can predict the world more and more deterministically, right? So that's actually what we talk about. In this sense, precisely the classical approach and the modern approach, data-driven, classical, model-driven. Now the sort of now the modern approach is data-driven are exactly the same thing, right? Except in the old days, we describe the structure using analytical models, right? We can write down equations. Or today we describe the model based on the data, which lies on those low-dimensional structures. And we try to learn those structures, right? And then what it boils down to, how do we learn those distributions, right? Especially from finite samples. We know our data lies on some low-dimensional distributions, a distribution with low-dimensional support, right? Let's, for now, just call them manifolds, curve, surfaces, right? Hence, we try to learn a better representation. Right. Why is that? Right. Because we want to build a memory model of it. We want to access the memory repeatedly. Right? We want to have very efficient access, organize the knowledge, separate what is the different, and the cluster what is similar. Right? Hence, the principle is always contrast what is dissimilar, contract what is similar, right? Cluster, grouping what is similar, and separate, partition, segment what is dissimilar. Okay? So you have a very structured representation of the structure of the data in the external world. We call this world model. We call this memory. We call this knowledge. Okay? Now, because of this, then how do we make this problem formalized as a mathematical problem? Then we must have a measure. We must have a measure, a metric. Tell me what I gain from this. Why make one representation better than another? Okay, it's a very basic question. If you don't have this, how can you compare which one is better? What do we try to gain from this process? In fact, we spend a lot of energy, right? Life spends billions of years to develop a brain like this. It must serve some purpose. It must make something better, right? Hence, one of the possibilities is that we try to make the distribution linear, right? What is similar, what belongs to the same group, the same cluster, make it linear, like a Gaussian. What is different ones, we try to separate them, make them incoherent, independent, even better. Okay? Geometrically incoherent, statistically independent. That's it, separate, right? So hence one natural measure, as I said, right, is so-called coding rate reduction, or the difference between the volume. Very simple, right? Don't be scared by all those fancy names, okay? Oh, rate reduction, do I have to know information? No, it's just the difference of the volume. Slightly basic, unifying way of measuring the volume of the data sets as a whole and about parts. Okay, as simple as that. Only when you try to do this carefully, you carry some scary names, like rate distortion and the rate reduction and so forth, right? You know, you can characterize. In the case of mixture of Gaussian, they have a closed form, right? We call it the rate reduction. Hence, if this has become the goal, if this is a metric we use, which unifying contracting what's similar, contrast what's dissimilar, right? It's actually capture that, contrastive learning, contractive learning, and so on, right? And you can do this, optimize this. And this become objective, then the natural way to optimize this through gradient descent. Then those operator, right? Those operator, the gradient of the operator precisely give you the reduced network grade, right? So this objective gave you exactly this architecture, right? Hence the white box deep network is exactly just to unroll the optimization. You have a clear objective. The network's objective is try to optimize that objective, right? Hence, the architecture derived from the gradient, or even better, maybe the contractive map, maybe the power iteration. You know, whatever hence, once you're in this domain, you search for the most effective operator to optimize, okay? That is a game for optimization. Leave that for experts of optimization people, right? How to optimize that. Then, but once we have such a representation, this we call auto-encoding, right? We do this is the PCA is doing this. Nonlinear PCA is doing this, right? All the people is doing. ICA is doing this, okay? And deep network is doing this. VAE is doing this in a heuristic manner, okay? But we make it explicit. Now, once we have learned such a representation for the X, we have a Z. But remember, this is still in some dimension Rn feature spaces. We still don't quite know where they are, right? Those are a bunch of subspaces. If the rate reduction did a great job, okay? You end up with a lot of pieces, subspaces, maybe incoherent, right? Remember, but that may still in a very general position. We still don't know where they are, okay? For example, even I tell you all the data lies on a single subspace, you still have to find it using PCA, right? So that is unavoidable. Now, but if I'm dealing with a bunch of subspaces in this form, I cannot do simple PCA anymore, right? How do I find this thing in this little RD, feature space? I have to generalize the process of PCA, right? I know I'm pursuing a data structure that is a mixture of Gaussian, a mixture of subspaces. Hence, generalize that, right? I have to go through from random initialization, try to converge onto the subspaces. Remember what the PCA is doing, right? Power iteration is doing, right? So you know that the Hilbert says, right? The Hilbert 这边讲过, when you try to prove a mathematical theorem, right? There are only two ways of doing it, right? One is work on the special example, special case, right? See, you're pursuing multiple linear structures. How about let's work out one, right? What's the solution to get the one first? You only have one subspaces, power iteration. That denoising process. That's an example of denoising, compression, right? Hence, the general case must carry similar characteristics, right? Hence, extend to mixture of Gaussian, mixture of subspaces. You know, the things we worked that out, right? Or the recent work of Qing and all those people, young people are working on this problem. And this family of denoiser, for this kind of family, if your target is a mixture of subspace, this score function, the denoiser, precisely has the form. For mixture of Gaussian, has the form of grade. Right. Hence, here, the structure of the operator is determined by the objective. I want to. Here, the structure of the object, the architecture of the denoiser, the transformer-like architecture, is decided by the distribution, the target distribution I'm trying to converge to. OK？ 对照知其然不知其所以然。OK？ 这就是所以然。Why transformer works in both cases, right? Now, in these cases, I start from random, try to converge onto 所以呢，这就叫条条大路通罗马啊。This is 罗马。OK？ Very structured city, right? You try to find it, right? Then everything goes, right? Different gradient descent, various expansion, various preserving, flow matching. You can give hundreds of names, okay? Every time you find a new process to approach that target, and you claim to be 10% faster, you give a new name, okay? Just like we assign different names to different roads, okay? If it's a faster road, your name will stick. If it's not, it gets forgotten, right? So that's the game, right? So this is actually the common game, right? So this is the main picture, right? One is we call representation learning. One we call the autoencoding. In fact, both are special cases of autoencodings, right? One is between distributions. Other one is also between distributions, but this one is, actually this is not 1-1, right? This is compression. This is almost 1-1, lossy, but almost 1-1. So okay, let's give you a little bit summary what we have done so far. So it's very, very simple. If you forget about everything I said so far, just remember those two pictures, and you remember 90% of the course, okay? And whenever you get lost, think about what we're doing there, okay? Encoding, decoding, diffusion, denoising. That's it. So yeah, the rest are just details, okay? Now, the next thing is, this is what have we done. Of course, why do we do this? The reason we do this is because it must be useful, right? We get a hold of this distribution X and get a representation of it. And also has a way to access the representation. I mean, by the way, this is called, incidentally, right? This is Xie Sanlin called the representation autoencoding. It's exactly doing this darn thing, right? Except here, this is learned from Dino, right? Again, Dino, we talked about last time, right? The object function is exactly similar to delta R, okay? Contrast and contract, okay? Either you learn this encoding in the open loop or the closed loop or autoencoding, right? Today we'll talk about you can also learn this autoencoding, either open loop, through Dino or autoencoding, we call it the MAE, or another closed loop, we call it transcription, right? But just settings. As long as you have data, you have it not computed, just optimize FNG, okay? Make sure it's consistent. Make sure it fits your data, okay? Fits input output. And optimize object function. That's it, right? There's no mystery about it. It's just how do you do which piece first or do them together. Depends on how much data, how much compute you have, and or how much time do you have. All right. And once you learn that, once you have something close to this, then building this is easy, right? So you don't even have to change the dimension. Whatever feature space is, you don't have to reduce dimension. As long as this guy has low dimensional structure, linear dimensional structure, it's very effective, very quick, very fast. Okay, and the form of them are exactly transformer-like. All right, the whole point of going through all this trouble is that I want to build a memory of the world, right? Because I want to use it, right? Now I can access it very quickly. My brain is organized. I have all this organized memory. I can use for prediction. I can use it for inference, right? 20. When I see something, I understand what's going on because my memory tells me there's a bunch of chairs, a bunch of people around in front of me, right? I quickly recognize that. Then if I wanted to talk to someone, pick anyone out of the crowd, I can do that. I can inference. Where's my TA? Where's some students I know in front of the previous lecture? Okay, I want to do inferences, right? Hence, but we saw all this practice, right? In the literature, or generative AI, discriminated AI, all this different data generation, image, text, and so on, right? All these different things, or completion, denoising, all the things, super resolution, all those medical images, all the things. What the heck is going on? Are they working on all the differences that are different? Or are they actually working on exactly the same darn problem? They're just the instances. Yes, they're just different instances of a single thing. You're trying to use the learned distribution to conduct inductive inference, okay? To predict what most likely the data should be based on partial observations, okay? We'll try to unify that, right? For example, right, we learned all this low dimensional, right? Either those distribution representation is analytical or deep empirical, right? For a deep network, right? Analytical, those are examples of physics, right? Or describing all the data, physical data, signals, what the equation they satisfy. Or images, text. We don't have an explicit analytical expression, but we can learn their distributions through diffusion, right? Through precisely the previous approach. We cannot write down an equation for it, but we can access it, right? Just like when we try to solve an equation, right? So guys, don't you realize, right? Even I gave to you those solution equations, how do you solve them? We'll talk about that, which goes through exactly the same process. Not that different from this, okay? 所以你看看，别以为对吧，拿了 equation 你就觉得很了不起，对不对？你解一解看 ，How do you solve the equation? Now you think about why Newton invented the Newton method to do optimization. Start with a random guess and do iteration to solve equations, right? Back to this. Nothing that different. Exactly same process, okay? Hence, we can do it for images, completion, all the tasks we have mentioned in early lectures, right? We use low dimensional structure, we learn those laws, we learn those structures. We use for regression, classification, denoising, completion, prediction, error correction, sampling, and they're all generation. They're all the same task, okay? Just the different, slightly different variants. The settings are slightly different, okay? We'll talk about that, right? But conceptually, it's exactly the same problem. Nothing else. Right? Hence, all the practice in the past decade, as we're doing now, is just exactly the same, right? All the classical approach, people do regression, linear models, start with Gauss, right? It's doing the same thing, or denoising, right? least square, doing the same thing. Kalman filter, Wiener filter, right? All doing the same thing. Okay. Completion, image completion, text completion, prediction. They're all doing the same thing. Okay. Using the structure. Now, what's the common problem? What is the mathematical formulate, right? What we talk about. See, here is the distribution of the data, right? It has very low dimensional structures, right? And they can be described by some equations or by a diffusion model, we can access it. Okay, that's it, some surface. Right. Now, usually what we see part of the data. What happened in the past, what's gonna happen next frame, right? Or I see part of the image, I get occluded, right? The y is a function of x. I see, okay. Usually, right, something's missing here, right? You don't get to see x precisely. So you want to find out what the heck is x? What is a complete x? That's it. All right. This will allow me to complete pixel or complete the sentence or predict the next word. Okay. Right. Or in physics, we know where the object is traveling. Right. What's the trajectory? We solve the equation. We know we can predict the orbits of the planets or the orbits of the rockets, so right? That's it. Or particles. So X may be a distribution, could be in high dimensional space, as I said, right? I said about repeatedly, in high dimensional space with low dimensional structure, with the probability, with the distribution has low dimensional structure, that behaves both geometry and the probability are very much the same. Okay? You can talk about distribution or they're just the low dimensional manifolds. So. And the geometrically low dimensional structures support, right? And then of course with some noise, right? Occlusion, the noise could be, in general, could be noise, Gaussian noise, smaller sparse errors, missing entries and so on. Right? Now, how do we go mathematically, what are we trying to do? We only observe y, right? Y equal to some nu. We try to predict what the heck is x, basically. Right? So there are several things I can do, right? There's several things I can do. One is that given y, I can try to sample whatever follows this probability. This is given y, x may be not uniquely determined, right? Still follow some distributions, but it's much more narrowed down distributions. I can sample anything that is not that distribution with some probability, I can sample it. I don't care. But at least it's consistent. It could have a chance to produce this observation, right? This is the least restrictive estimation. What likely x is, okay? I just sample anything that could have produced this observation. I'm happy. Or I can see what is all possible x, what is average? Mean. Could have produced the observation. All the possible x, I take an expectation, 对吧？加权平均一下 right? Weighted sum based on their probability. I add them together. Right? We'll see what's the difference, okay, in a second. You have to visualize, right? They're all plausible, okay? All plausible guess what the x, most likely x have produced the observation, consistent with my observation. Another one is that among all possible x, right here, see, in y, given y, the x still has this distributions. Some are with higher probability, some are with smaller probability, right? Some are dense, some are less likely, right? So maybe the most likely x is I want to choose the peak, right? Imagine here, this is a density function on y, right? So I want to pick the most likely x with the highest probability that could generating this observation. This is called maximum, right? A posterior estimation, right? This is usually what we want. But in order to find this darn thing, see, this gets increasingly harder, right? At least if we are hand-wavy things, right? I just give me the y, I just get anything that could have produced it. With some probability, I'm fine, right? This one requires a little bit of work. At least to compute this, I have to properly sample multiple x, which could have produced also based on their frequency. Each x may have a frequency 0.1, this x, or 0.2, that x, and then I do a weighted sum, right? Then likely to see what is the average could have produced this. At least I have to do more samples than just taking one, okay? This one is the hardest, right? This one I have to traverse the whole landscape, find which x has the highest possible probability, find the peak of the whole landscape, right? 至少概念上啊 conceptually, you know the difference, right? Right. So this basically you pay a little bit more price by trying to look for the most probable solution, right? Understand? So this is a mathematical problem. So this is not a unique problem, right? There's going to be different branches, right? They all have something to do with try to guess what x is that agree with this observation. And x has this kind of prior, okay, disputed in such a way. There are two pieces of information, right? First, x dispute like this. Second, you observe something. This is equation. There's two pieces of equation to pin down x. Well, what is the common approach? Right. Right. What is machine learning? Right. In the past 10 years, right? The popular approach is that, you know how things started, right? Let's have a lot of pairs, x and y. I care about x and y, okay? Imagine ImageNet, right? Right. Image and class label. Image. So a common approach is that directly learn this conditional distribution. Learn a mapping, learn the density given yx or x to y, okay? So I have a lot of pairs. In fact, this way, honestly, I don't even know what it really, they claim they're learning this, right? But it's basically approximate this, right? Remember, you can use the neural networks to learn, you know, right? ResNet to learn the probability of the class label, right? Then do a soft mask, then assign that to call, right? So that this is 1000001, all these k classes, so you do sort of a probability, right? The vector, and you do a soft mask, that's the last layer, and that's very much estimating a probability of y, okay? At least heuristically, okay? Pretend to learn something like this, okay? This conditional probability with the data. And then you learn a classifier, right? And or just learn just directly mapping, right? Not even try to pretend you're learning a distribution. Fine, I'm just learning the mapping, okay? Deterministic, just fit the neural networks to least square, right? Optimize some loss function, right? Directly fitting. Some people do this, right? It works. We call this end-to-end approach. Very popular, right? In fact, this is probably the most common practice. Most people do this, right? Because I just try some neural networks, get enough data, right? Many data. I can always tweak, getting better getting better F and G, right? If one layer is not enough, 2 layer, 3 layer, deeper, better. Or if the data set's hundreds is not enough, thousands, millions, 10 millions, billions, right? Fine. 所以吧，这就叫什么？我们有时候说这个人傻钱多啊，这个你就可以做这种事 ，right? It's not bad, but it's really not something very straightforward. Okay. So what is the drawback? Actually, this explains why there are so many papers, right? Because whenever there's a task, classification, segmentation, right? Recognize different classes, color segmentation. Right? Object segmentation or classification. Whenever there's a class, I only have to label a bunch of data. What is input, desired input, and output, and do this. Whenever there's a new pair, new task, I can collect a new set of data, right? I can train a new neural network and publish a paper about it. And even better, someone follow me will say, oh, I do this tweak about the neural networks. I get 2% better. And there's another paper comes in, oh, I add a few more data. I augment data better, right? I get an additional 2%, right? So hence, every specific task, you can write a bunch of papers, right? Every data set, you can write a bunch of papers, right? You can pretend you're solving this problem better and better, right? And then you say, well, let's scale it up. 10 million, 10 billion, right? or bigger models, right? Hopefully get this problem, this task tends to have a slightly better and better performance, right? Actually, that's what people do with this. Right? And also the network is kind of designed empirically because there's really very little information tells you what this F and G should be, okay? Well, try any neural networks, tweak it, because maybe every input output may have a different characteristic, may requires different architecture. God knows what it is, right? So it's very hard to say what the operator should be, okay? Then you try. Wider, deeper, more parameters, this tweak, that tweak, this thresholding, that thresholding, this normalization, that's normalization, this dropout, that dropout, okay? It's up to you, okay? Try, right? Try different recipes, different training recipes, right? So this is a problem. Hence, every specific task you train. That's also why there's so many papers about reinforcement learning. Every task, you design a loss function, you train, and you show it works, right? By the way, this paper like this has zero contribution to science, right? It's just maybe useful for some practice. That's about it, right? It's exercise for all of you. Should be there in the future. Should be homework. It's your exercise, right? It's like you learned calculus. You apply to different integrations, okay? No difference than that. Now, what is a better approach? Right, let's assess the situation a little bit, right? So for this task, X and Y, given X and Y, right? The conditional probability is usually easy. Well, we'll talk about that in a second, right? It's easy if this model is given, right? Sometimes this model is given. For example, I disguise something, right? I know which part of the image I saw, right? So this H function is explicitly given. At least that part is easy to fulfill. Given X, what is Y, right? But sometimes it's not, right? For example, classification. Classify natural images to class labels, right? That mapping is not given. Okay, you have to learn, right? So keep that in mind. So this is one piece of the puzzle, right? And the prior is actually important, right? Right, because why? For classifications, for example, if you don't know the prior, can you stick an arbitrary X into that to get a meaningful classification? You know the space of images, right? Pixels, space of all pixels. Mass majority are not natural images, okay? If you stick into an arbitrary X in there, you get a garbage, okay? Hence, even to get measurement model correct, you have to apply to give the right X, okay? Sample the correct X so that the H become meaningful, right? Hence, for many tasks, right, you need to know what the X is distributed, right? And if you do this end to end, this information was disguised, right? If you do this, you actually don't learn the distribution of X, okay? At least not explicitly. Right? Now, can we get this to learn? Second, now, of course, a lot of inferences, we give Y, we want to find what the X is, right? This is the posterior. You try to find that this is the 后验概率，对吧？先验啊，后验概率 can be derived by a Bayesian rule, right? If you just write down, this is the Bayesian rule comes in, right? So, given Y equal to nu and what is X equal to psi, this is the probability, right? There's three terms. This is observation, this is prior, this is normalizer, right? Chance. Everybody should know this. Right? This is from Statistics 101. Right? So now here you can see if we break down things like this, there's something very interesting, right? So at least the prior part, we'll talk about this later, right? This is observed, right? This part is usually okay. We'll talk about how to compute this, or this is a nuisance term. This has something to do with observation. But for those two terms are more important because it has something to do with X, okay? Both has something to do with X. But this term, you notice that, this term has nothing to do with H. Basically, the prior distribution of X is a piece of information has nothing to do with what I'm going to do with my memory, what the specific function, task I'm performing. Remember, it's something shared by all tasks. 所以我们的世界模型 our word model, our memory, our visual memory, our muscle memory are here. I'm not doing anything. I don't know what I'm going to do in next second, okay? But the memory is there. That's my X. So if you tell me to do something, pick up a cup of water from next door, I know how to do it, right? I don't have to learn like a baby. Don't even know how to walk. Don't even know how to pour waters, okay? I don't even know what a water bottle looks like. My visual memory, this X will enable me to give me a task. I know exactly what to do, right? So this is PS is if especially once I learned as a structured representation PZ can be shared by all tasks. I don't know what next second. I can support recognition, segmentation, generation, completion, occlusion, prediction. So right, I don't know which HJ I'm going to use next time, but X is a common. Understand? 明白我意思吗？对吧？ But this formulation is not, right? Hence, now you understand, right? In early days, when we talk about the redo network reduction, right? Remember, this is a theory called the information bottleneck. You try to do classification, you try to extract the most relevant feature to help with classification. But that feature is task dependent. Hence, information bottleneck is a wrong approach to understand what deep network is trying to do. Okay, in learning something, you try to learn feature that is, or representation of the data that is task specific, task dependent. Honestly, I don't call that feature of the data. It's a feature for the task, for why. Remember? Right. Hence, right, there's very different things. You are learning a feature or representation for the X, for the data, or you're learning something relevant to the task. It's very, very different. Now, if you do this, then the architecture, G and F, are all specific to that task. It's very hard to apply that to other tasks. Of course, you can say, in early days, people say, we can do transfer learning. People find some of the networks are transferable, right? Really? Are you kidding? Yes. Softly, yes, they may be useful, but there's nothing guaranteed, right? Transfer learning was very popular. Right? People feel that they can transfer, but they don't understand what the heck, which part is transferable. They try, right? 大概10年前，对吧？热得不得了。Everybody is, we can transfer, we can transfer this, we can transfer this. They don't have a theory understanding. Guess what's now? Who's still doing transfer learning? Good luck. 对吧？所以理论会告诉你们，对不对？ What is transferable? This is transferable, okay? This part. Or, of course, for tasks that's similar, you have learned some Y, H are similar. For a cluster of similar H, yes, that may be transferable, right? But you can make it very formalized, very rigorous, right? So hence, a wider approach is to try to learn a common structural representation of the world, right? From data, for any all tasks. In fact, that's what our brain is doing. Right? Our baby, since we grow, the baby playing with toys, observing, interacting, right? They build the memory. They don't care what task. Every single task, every time we walk, every single touch, we're building our model, our muscle memory, our visual memory better and better. Okay? Yeah. In a self-supervised, in an unsupervised, in a supervised way. We all contribute to better visual model, our memory model, and to make X better, okay? We always prepare our memory in a structured way so that when there's a new task comes in, when there's a new H comes in, we can use X most efficiently and most correctly, okay? That's transferable. 所以我们经常在讲，对 对吧？什么叫可泛化这个词儿 ？You know, generalizable is a very vague term. Okay, at least in my understanding, there's at least 2 levels of understanding generalizability. One, right, is precisely a common piece of information can be shared among multiple tasks. Then this is it. This is one level of generalizability, 可以泛化的东西。OK， 当我有一个共同的 memory， 这个 memory 可以 serve 不同的任务。This is one level， 一种可泛化的概念。What is the next level? PX may not be the best. Who can guarantee the distribution is right? Is complete. Your memory is complete. What is the next level 可泛化 generalizable? Make sure you have mechanism to update the PX whenever necessary. Okay, when you see new piece of information, you can expand that memory. Okay, that is truly generalizable ability. 明白吗？所以你们前面也听到，对吧？那才是真正的 intelligence 在做的事。Right? Share knowledge among different tasks is just one notion of generalizability. And be able to even update, upgrade, expand your knowledge, the distribution, make it better, make it more complete, is the true level of, right? Because this allows, have this mechanism, you can start PX, start from 0, from knowing nothing. 知道吗？所以这是今天想 clarify 啊，2层啊，所以不要通用人工智能，通用个啥呀，对不对？你们先把它讲清楚，从数学层面啊，技术层面把它讲清楚。What do you mean by that? Okay, don't use the natural language to specify your problem, right? Because natural language itself is a problem. Okay, when you try to comes down to specify your what is the mathematical problem behind your questions, right? Kind of what you try to understand. Right. Now, this understand, right? Now we suppose we have X. We have X now. Remember, this is 2 pieces of information. Always remember, one is a piece of X, one is the observation model. Okay, we always play with this 2. Okay, this is the only 2 pieces of information you have, right? Now let's work about the first one. See, this is my conditional distribution, right? Second one, sorry. Right, this is what, given y equals something, the conditional probability, remember, x is very low dimensional, right? So this is actually in some spaces. This is all possible x agree with y equal to nu, right? So now I'm trying to do inference. 对吧？第一个 inference, remember, is the simplest one. Oh, sorry, the most relaxed one, all right? So I just find me any sample on this distribution, right? See, this is a conditional distribution given y of x, right? See, that's it. There's a higher probability, right? You can see this is a lower, you can think about there's like a Gaussian, right? Here is a dense and a more, sparse, right? Now I say generating any, but this is a support of the distribution, meaning that any point on this curve has a chance and also agree with this observation, right? Can produce y. And this is a conditional distribution of x given y equal to nu. Okay, so any point on this curve has a chance to produce nu, right? Can give you a feasible solution basically. And then just draw one, right? Doesn't have to be the highest probability. You're just lucky, right? You just draw someone, right? Of course, more likely the points close to here gets drawn, right? But there's no guarantee. Okay, sometimes if you are bad luck, you can even draw a point like there, right? It's okay. Anything is possible. So this is what this one will do. We call it a sampling, right? We do a sampling. The second one is that, well, let's do weighted sum, right? This one has this probability, this one has that probability. Let's do an average of all the probability. This is maybe 0.5, 0.1, 0.01, and so on and so forth, right? Every point has a weight. Then let's just do an average of that. That's what the expectation is. All the points do a weighted sum, 对不对？ the expectation of it. So what it will look like? This actually will be here. 为什么？因为这是个曲线，对不对？就像一个圆一样啊。If you have a circle, what's the mean of all the points on the circle? The center of the circle, right? So it's outside of that circle. So you should expect we are doing expectation in the higher dimensional spaces. The expectation might be out of that distribution, out of the support. 待会儿我 see 在图像里面会发生什么事儿，好吧 ？If you do this, you get. But this is still okay, right, in high dimensional space. Now, but the one we really like, is that among all this curve, right, among all possibilities, we want the one with the highest probability, 对吧？概率最高的地方啊 ，that's what we want, right? But then we have to solve an optimization problem along this curve, right, among this distribution. Right. This is a little bit hard work, right? And fine. Well, of course, you already know how to do it, right? So, let's do, at least in this way, we do gradient descent. We follow the gradient and try to get a higher probability, but fine, right? As long as you have enough GPUs, you can do that, right? So enough data, enough GPUs, you can do that. No problem, right? You still can do it with some price to pay. Right? Now, at least conceptually, I want to ask you a question, right? So when these two are the same, very much the same, 在什么条件下，对吧？ The conditional expectation and the map, maximum a posterior. We call this is called a map. This is called, because this is a posterior distribution, right? So this is called a maximum a posterior. The point where we reach the maximum probability in the posterior distribution. Right. When those two conditional expectations become similar. Well, I already have the answer there, right? When this is almost Gaussian and this is linear. When the curve is not curved, it's straight, right? 所以它的 average 还在那个 curve 上，对不对？还在那个 surface 上面。所以找那个 surface 是线性的。If the surface is actually linear, then the average will at least stay in that surface. Okay? But also in terms of density, of course, on the surface is density. But if it's unimodal, like Gaussian, then the mean will be very much in the center. The highest peak is also in the center. Okay? So those are the conditions you can see. So it's not that those two are always different. And in fact, when you really see that, also now you understand, right? Why the heck we want to make this linear and Gaussian? The more here, the more you make the feature piecewise linear, piecewise Gaussian, solving maximization is easy. Finding the most likely points, do average sampling. Do sampling is easy, okay? It's fast, quick, and also accurate. If it maintains as a curve, good luck, right? Try to find the maximum points along the curve. Good luck with that, right? Right. So now you see, right? There's a lot of things why we want to make our distribution linear and Gaussian, okay, in the high dimensional spaces, because we want to make those computation easy. Now, how do we do map, right? And another thing we like is that this looks to do sampling, have to do average, but this one has a flavor of optimization, right? This we can see, to find this psi, this is actually, we have to maximize the posterior distribution, right? Solve this optimization problem, but let's use the Bayesian law, right? There is actually take a log, because this is monotonic. Log is monotonic, right? Take a log and become a sum, right? There are 3 terms, guys. 1, 2, 3, right? But they're all multiplications. Take a log, it becomes log of this plus log of this minus log of this. But this one has nothing to do with psi, right? When I do argmin on psi, that term is a constant. Let's drop it out. So I only have 2 terms, right? Upstairs, the 2 terms. Depends on psi. I want to try to maximize. Right? Now, how do we compute? Maximize this? Well, everybody is happy, right? Well, maximize, everybody know. Let's just do gradient descent, right? Gradient ascent is maximization. So it's gradient 爬坡，对吧？ Let's climb the hill, right? Everybody knows. If things were that simple, 对吧？是这么简单吗，同学们 ？Let's pause for a second， 对吧？是问题这么简单吗？就是算一算嘛，对吧？大家想一想这个难点在哪里 ？What's the difficulty here? Right? What's the difficulty here? All right. The difficulty here is this guy, right? This guy has a low dimensional support, right? And this is the space of what? X, right? Px is here. Remember, in the beginning, we don't know what X is, right? We may be here. The gradient means I have to take the gradient of P of X, right? But what's the P of X here? 0. Where's the gradient? Which direction to go? You don't know. The gradient vanishes outside of the support, right? So this is not defined everywhere. Okay, that's the problem. You don't know this guy everywhere. 那怎么求导呢? That's one way. What about this guy? Right? This guy, you think it's simple, right? Looks simple. We have y equal to ax, right? Y equal to h of x, right? We have this thing. But also, again, guys, this x is not defined anywhere, okay? Hence, the conditional probability may look like this. When you are, right? When you give x here, you don't know, right? When you have here, in this case, you don't know where to actually preserve. Again, you cannot differentiate everywhere, okay? It's not everywhere defined. Even this term, condition on given x, this side, if it's outside of the support of x, this is maybe not even defined. How do you take the derivative of this guy? Right? Think about it. Right? 所以写下来很容易啊。所以经常我不是说嘛，原来我也 criticize 过，对吧？ The machine learning, a lot of practice is very bad. That's why in practice people try. They don't know, they don't understand what is wrong. Okay, since try many different things. In the past, all the NeurIPS paper, right, start with, let's minimize Kell divergence. Let's minimize this distance, that distance. And most of the time, they're not even defined. Let's do this gradient descent. Let's compute this, right? Let's compute this. Oh, I am computing this. Are you ready? Are you kidding me? Right? This is not even defined outside. What the heck are you doing outside the data? Right? Oh, let's approximate. Let's add another loss term, right? And another term, x to approximate this, right? 大家在瞎干这个东西，对吧？做的。Now let's rethink. We'll teach you how to do this, right? How to do this in a principled way, right? At least in a conceptually correct way, right? So let's rethinking this question. Let's rethinking this problem. Rethinking this problem, okay? Suppose we're God, we can do everything, all right? Just conceptually, let's try clean up the mess, right? Suppose what do we want to do? So the data x has some no dimensional structure, right? Has this. Now let's define a function. We call it, you can call whatever it is. You can call it an energy function. It's any x. This is defined on the entire space of x, okay? That's a key. This is a function f is defined everywhere in that space. Entire RD, okay? Not just on the support of the distribution. It's everywhere in the space. But to pick any point, the capital F is the distance of that point to the closest point on the structure. Okay, that is well defined, right? 可以定义吧? I told you, right? I'm God, right? I define whatever I want, right? Suppose I can compute it, right? I define this function. I suppose then this function is defined everywhere on the entire space of X, okay? And also, this equal to 0 if and only if the point is on the support, okay? Precisely on the support of the distribution of X, a true distribution of X, okay? Easy, right? So this is by definition. And hence, basically, every point is on the distribution of X, a true distribution of X. Then satisfy this as a constraint, f x equal to 0， 对不对？变成一个 constraint 了。这就是牛顿方程，对不对？ This is law. What x satisfy? So, right? You can pretend it had analytic form, right? But it's a function you cannot write down, okay? But it exists, okay? It's a function exists. Such a function exists, at least if the manifold, if the support is benign, okay? Such a function exists, and this is the equation. Describe the world model, all the laws that x has to follow, okay? Fx equal to 0, okay? That's the equation x satisfied. Now, what about our observation, right? Observation is, remember, y equal to h of x, right? Hold on. Yeah, y, right? This is a y equal to h of x plus w, right? Hence, the h of psi minus nu should be equal to is Gaussian, right? The difference between my observation and the true x should be follow the Gaussian distribution, right? So hence, to find what is consistent with my observation, I have to solve this problem, right? Find the most likely psi, right? Follow this, satisfy this constraint for all the psi that lies on the surface, and also has the highest likelihood based on this distribution of W, noise. Noise is Gaussian, right? And so this is actually solve this constraint optimization problem. 这个 is defined everywhere, 对不对? Because here, first of all, psi is restrict into the surface. This is well defined, and this function is well defined as well. And also h psi, because once psi satisfies the equation, h psi is well defined, and only deviate from my observation by a w, which is a Gaussian. This is likelihood of a Gaussian, right? Very simple, right? So this is an optimization, is a well-defined problem. Right? The question is, how do I solve this? 这个是什么 problem 啊？同学们看到，假设你知道 f 啊 ，here already know how f. What is the problem? This is a constraint optimization problem, 对不对？ How do we apply constraint optimization problem? How do we solve a constraint optimization problem? What is the most popular method? Lagrange multiplier, right? Actually, if you know a little bit better, right? Actually, Lagrange multiplier is just a method. It's not an algorithm, right? The actual working algorithm to really do Lagrange multiplier correctly is called the augmented Lagrange multiplier method. Okay? 正确的方法是用这个，对不对? Not only using this, Lagrange multiplier is using this one, right? Do a minimax with lambda, right? X and lambda. But actually, the true one, the correct one is actually doing this. Add a penalty term, quadratic penalty term. This is called augmented Lagrange multiplier method. This is the method, okay? In practice, in algorithm. This gives you a working algorithm, okay? This one, anyone can tell you why Lagrange multiplier method does not give you an algorithm, working algorithm. It only gives you a condition for the optimality. Certify the optimality of the solution. Do you know? Anyone know? 所以看来你们用了这么多优化，对吧？什么 Adam 下载下来，对吧？呱呱呱呱瞎折腾，对不对？都是叫知其然，完全不知其所以然。为什么要有这些 momentum term？ 为什么 minimax Lagrange method does not give you a working algorithm？ 有没有知道这些答案的？所以同学们啊，老实一点啊，谦虚一点啊，啥都不清楚呢啊。 Lagrange multiplier only give you a condition at the optimality point. Certify whether or not that point is optimal or not. Does not tell you anything what's in the neighborhood. 如果你不在那一点上 this condition tells you nothing. Okay? 明白吗? It's just a condition on the point of optimality, certified optimality. It does not give you working answer. If you're off that point, actually even those gradient does not give you an idea how the word to go. Okay? The minimax actually does not necessarily lead you to the station points. Hence you have to add this term. All right? 这是80年代很多人在 work on, 对吧? And what do you do? See, you want to enforce, right? So here you see intuitively, first just intuitively. Turns out, in fact, if you don't have this term, what is called? 60年代非常 popular， 没有这个 term 叫什么？这个方法叫 heavy ball method， 对不对 ？Barrier method， OK， 对吧？有了这一项叫，没有这一项叫什么 ？Lagrange method， 对吧？Lagrange multiplier， 这两项加在一起叫 augmented Lagrange multiplier。啊 ，together 缺一不可，两个在一起才 work。OK，turns out， right？ 好，那么just use your imagination intuitively，right？ 没有这一项 ，what is this doing when mu is large, right? So you wanted to make sure first of all this has to be small, right? This is the least square, and this term when mu is large, which means that this term should be getting smaller and smaller, right? When mu is infinity, which means that this term should be almost zero, which enforcing f psi equal to 0 almost, right? 所以这就叫 continuation mu， 看 mu 要不断增大的。So this is actually not a single optimization. You have to solve a family of optimization. You have to increasingly get mu larger and larger. You start with some small mu, solve the optimization, find the psi star, start with that, get mu bigger. Make mu bigger, then solve another optimization. So it's a sequence optimization, get you closer to this problem. So it's kind of a sequence of soft. 对吧? So you can see, think about this, right? This is where fxe is, right? So this is actually when mu, for fixed mu, right? Complete the square. 你把这个平方一平方 you get the expression like this, right? So basically f can be at this distance. The smaller mu is, the distance of psi can be further away from 0. 对不对? 这个 term only when mu is large, f psi has to be closer to 0, right? 而且 mu 这个也很大，对吧？你看 mu 大的时候，不光是让它的 mean 接近 0, the distance to 0 has to be very small, and also this one gets large, weight gets large, right? This gets enforcing f psi equal to 0, closely, right? So this is actually called a continuation method. It's very popular in optimization. So even basically, even your f is analytic form, 哪怕我给了你物理方程，对吧？哪怕你给了你牛顿方程 if I gave you the Newton equation, in order to enforce it, you enforce this way if you want to compute the optimal solution. So even f in the analytic form, you have to use it in this way. In the continuation, you cannot enforce fx equals 0 immediately. You have to relax it. Right? Make it further, gradually make sure things converge on the curve, on the constraint. Okay, this is called the continuation method. Numerically, this is always, right? This is actually give you a working algorithm to enforce the constraint, most effective one. Turns out mu goes to infinity is actually just a theory. Turns out you don't need to do it. You actually can prove mu only as long as mu is large enough, this always can enforce fx equal to 0 precisely. This is very interesting, okay? 你不用把 mu 增到很大，增到无穷，理论上是不用的啊。只要 mu 到足够大，这个 constraint 可以become precise. It's a very interesting theory. There's a very deep theory behind it. Okay, it's called the augmented Lagrange multiplier method. Okay. So check it out. Right? Then. Actually, in my previous book, I featured that, but not the entire theory, but at least the method was captured. What's there? All right. So this is actually now you can see here are the two things, right? What this term is doing? This is, sorry, there's this term, right? This term is exactly hx equal to mu, right? When w is 0. Right? When w is not, this you can think about there's a Gaussian, right? So this is a quadratic function. This term is what doing? It's doing denoising, right? Pushing things closer to the denoise. So what this term is doing, this is enforcing fx equal to 0, right? It's actually doing continuation. Hence, this is exactly like, oh, I cannot satisfy fx equal to 0 immediately. Let's add some noise, add some error to it, allow some error, enforce the constraint in the soft way, right? Hence, denoising continuation geometrically is doing exactly the same thing. 大家开始明白了吧？对不对？当你有 observation is also a constraint, right? This is equation without W. This is exactly equation. This is also equation. Basically, you try to find X satisfy two sets of equations. And you cannot enforce, you don't know the solution because you cannot solve them analytically. There's no closed form. You do it numerically. How do you do it? You do it through continuation. Gradually enforce the constraint. Okay? And that's a universal approach. There's no exception. Doesn't matter. This piece or this piece, you have analytical or non-analytical expressions. This is unified approach. You have to do this. Okay? There's no alternatives. Unless some set of equation has a closed form solution, which is, by the way, is extremely rare. Forget about that. For the rest of your life, forget about it. That will never ever happen. Okay, you have a set of equations, or you know f of x, you know y equal to h of x. You can find a closed form solution for that. No, forget about it. Newton already gave up 300 years ago, right? You should give up. Okay, that's why he invented Newton's method. That's why Gauss invented optimization. Okay, as I told you, right? Great mathematician cares about the computing. They want to compute. They don't want to just satisfy just for the cases they can find closed form Pletty equations, formulas. Okay, those are useless. The most useful part is here. And now you can interpret it, right? There's people call it the energy function. In fact, now you can name it, guys. Do whatever you want, right? Some people call this energy function. Hence energy minimization, like Yang Kun, right? Now you know what he's talking about. Right? But for us, it's just stupid distance function. Right? Now we can interpret it, right? See, now you can interpret this. You can minimize this as a quadratic form. So both are energy functions, right? They both has quadratic form. You can think of it both just energy minimization. Only that you have to worry about the weights, right? The weights has to get enforced. And also you can, in terms of, this is just another map, right? This is your prior. This is observation. This is exactly doing map estimation, right? Just where we started to be. And now, what's the difference here? What's the difference between this one and this one? This is also map. We say, yeah, this is also map, right? What's wrong? What the heck? 我们刚才做什么了，对不对？为什么这个不行，那个可以呢？ What's the difference between this map and this one? This is defined everywhere, okay? This f psi is defined everywhere, works in the entire space of X, right? This f is everywhere defined, okay? This one is not, okay? This one you cannot compute. This one, if you have f, at least you can compute, okay? Know the difference? Okay. And when mu is large, you can let h hit psi at any time, any place. Remember, h only applied to psi that is really meaningful, right? Feasible. But in this case, once in this formulation, as long as you make the continuation happen, makes mu goes to large. This eventually gets enforced. Psi equal to f, psi equal to 0 will get enforced. So this one will be feasible. This will solve give you a feasible solution. Remember? So you don't have to worry about that part. Now, there's any other thing, right? So notice that we change between mu between 0 to infinity. The distribution looks like this, right? It resembles a de Sitter process, actually. Right? We let the x on x, right? X is on x. We let it diffuse. We let we can go further away from f psi equal to 0 when mu is 0, right? This can be very, very far. You know, 远离罗马, right? It can be very, very far. Only f psi equal to 0. That's home, right? That's Rome. But I can start with very, very far. Gradually make it closer to Rome, right? 离它很远，然后慢慢压回去，慢慢把那个 constraint 收到这个 surface 上去 ，right？ 这个过程像什么 ？This is exactly diffusion denoising process. You make mu very small, you leave away, move away. Psi come very, very far. Make mu very large, get back to the surface, get back to home. All right? So this is exactly the. Now, at least conceptually. 所以现在大家来想一想啊。这有什么用啊？我 F 不知道，但是 I can play with it. Right? This gives me another piece of information you probably don't remember. In the diffusion denoising process, we worry about the time frame. What's the step size, right? Now there's a very interesting answer. Right? Suppose I can define such F, right? Then look at this term. What does this look like? 这一项很好求嘛，对不对？求导。log 对吧？对这个东西求导好求吧？2次对 psi 求导，对不对？大家都可以求吧？假设 f 是可分的suppose f is differentiable. Take it looks like this, right? Everybody can do this, right? See, mu is some constant. This gets large. This is almost like the temperature. This looks like the time. Okay, mu is actually fixed. Now, think about, right? Mu is getting small, right? And look at this. What is the expression? This actually tells me. So this is the f of psi at any psi, right? So the closer I get into the surface, right? This is the distance. Remember, this is actually give me when phase large. When mu is large. This is very much close to 0. Basically, this term is very much a distance of psi to the surface, right? Give me the distance. You can see at any point, at a certain distance to the 0, at a certain distance f psi, this is a gradient. The gradient should be scaled by how far you to that distance. 什么意思？离家越远，步子快一点啊。快到了 surface 步子慢一点。So your step size should be proportional to the surface you try to land on. 是吧？你越接近，你的速度是跟你的距离成正比的 ，proportional to the distance to the surface. Okay, that's your speed control. This is natural scaling law. Does anyone know 为什么苍蝇不会撞死在墙上？蚊子不会撞死在墙上。你 constant speed, right？ 苍蝇飞得很快的，为什么它不会撞在墙上呢 ？How did it land？ 动物almost all birds land on anything based on this law. You can prove this gives you a smooth landing. All the animals, almost all animals, their eyes looking at the surface land on it. Precisely the speed is proportional to the distance to the surface. Very rigorously. Hence they land very smoothly on the land. Give you most fast and also smooth, safe landing. This is the universal law. 就这么简单based on energy 有很多物理的解释微生讲。 对，最小功、最小能量等等啊，非常 smooth landing 啊。It's very simple. Right? So even this one, now the question is that if you can, okay, I don't know how to compute. I mean, most of the stupid denoising process, but if you can compute, right, estimate every point how far you're actually from the distribution you are denoising against, you have a perfect scaling law. You scale your gradient at that point based on the distance to the surface, right? If you can estimate that, you get a very, very smooth, fast convergence, right? I don't know how to compute this, well, but if you can, this is what you should do, okay? See, theory tells you what you should do, what is the best to do, right? 明白吗？啊 Rather than try, right? Oh, flow matching is very, very popular. Everybody using it. Oh, this is the last bandwagon, okay? Let's everybody do it. Let's write another 100 papers about it, right? This is the best partition, right? Discretization. Are you kidding me? No, it's not, okay? This is the final one. Okay, anyone get closer to this, you're done. 明白吗，同学们？早着呢，对吧？所以一会儿来啊，什么 virus preserving，就大家有些取个名字啊，这个好像比原来快一点啊，赶快大家都要用吧，对吧？赶快到 Hugging Face 再下载来用一下，对吧？这个上面再改一改，提两提三提，对，加快速度就对吧？再快个1倍啊，这发一篇文章啊，快2倍又发一篇文章，对不对？sample 少一点，用的数据少一点啊，或者这个对吧？又一堆的文章啊，现在最热的是这个什么的吧，对吧？一会儿是这个 virus preserving 啊 quadratic term， 一会儿又是这个 matching flow matching， 一会儿是这个对吧？不同的 schedule time schedule， 不同的 discretization， try guys， right? Discover something universal, guys. All right, something is not that hard. Okay, it's not that deep. Actually has been very classical method, already tells you what you should do, right? In principle, at least. Now find how to do it quicker.